Okay, so thank you all for joining today's California Dreams Technical Seminar. We have Professor Chi-Wei Wong. He's a professor at UCLA and as Professor of Engineering. He does a lot of work on ultra-fast precision and quantum measurements in mesoscopic systems. And he prior to joining UCLA, he was with Columbia. He was a tenured professor at Columbia. He is elected to the National Academy of Inventors. He's a member of the National Academy of Inventors, and also to the American Association of Advancement of Science. He's a fellow of APS, IEEE, OSA, ASME, and SPIE. Quite a number of charters there. And he's also the recipient of the DARPA Young Faculty Award, NSF Career Award, Google Faculty Award, NIH Early Scientist Trailblazer Award, quite a number of awards. And he has his BA from UC Berkeley, BA and BSc from UC Berkeley, and MSc from MIT, and PhD from MIT as well. So let me welcome Professor Chi-Wei Wong to give a talk on the precision chip scale laser frequency microcombs at the fundamental limits. Professor Chi-Wei Wong, the stage is yours.
Thank you for inviting. Good afternoon, everyone. It's a pleasure to be here. In the next 50 minutes, I will update you on our precision frequency combs at the fundamental limits. We have several discussions as part of DREAMS. Happy to examine some of this and expand further for applications for the team. Today's seminar will speak about 4 key topics. For example, we'll start with how do we achieve very short pulse mode locking on a planar silicon nitride chip. For example, how do we get to 74 femtoseconds, near transform limited, at a clocking rate of 116 gigahertz? How do we achieve broadly tunable over 2.8 octaves from a few hundred gigahertz all the way up to a few terahertz coherently in a single device with very low phase noise? The second topic I'll describe to you is how do we achieve what we call full comb stabilization? I'll describe what a frequency comb is. How do we get full comb in the sense the dual degrees of freedom? That was part of the Nobel Prize in 2005. How do we stabilize this on a single chip to the level of 2.7 parts per 10 to the power 16 at 1 second integration time? I'll describe to you also how do we do metrology of this noise, for example, phase noise for single sideband phase noise for the local oscillator, at the level where we actually reach the quantum limits and also thermodynamical limits at room temperature. It is non-trivial for these measurements. To my knowledge, there's 2 instruments in the world that can reach maybe about 150 dBc per hertz at 10 kilohertz offset for your radar X-band. How do we get below that? How do we get to minus 160, minus 170, even minus 180? How do we measure that at room temperature on a single chip? I'll describe that to you today. I'll give a reference, for example, at 89 gigahertz. How do we do this femtosecond metrology on chip? In the 4th topic today, I'll describe to you also as a reference clock that we can achieve, or the community can achieve, lasers at the hertz level. How do we achieve that on chip? And we like to think of this line width more precisely in terms of a frequency noise power spectral density, a frequency noise PSD. How do we achieve sub 10 hertz per root hertz compact lasers at your thermorefractive noise limits? There are different thermorefractive noise limits, different models of that. I'll describe a few today on achieving that on a single resonator. On the bottom left, you see 2 cartoons. One is generating short pulses. So the framework is you start with a continuous wave light coming in from the left, and the output are this very short, precise pulse trains at multiple repetition rates of your radio frequency. Again, all the way from 1989 gigahertz, 116 gigahertz, all the way up to terahertz, completely tunable. You also notice that the resonator is non-uniform. This is on purpose. There are some adiabatic designs that we put in. The nonlinear dynamics of this is supported by various DoD programs. How do we generate this with high efficiency, high power, full tunability on a single chip? In the middle, I'll show some work on the dynamics of this. This is a second harmonic generation. How do we understand the localized solitons, spatial temporal breathers in them? How do we purposely put in defects so that, for example, I can reach a high harmonic of your fundamental? On the right are some of our contributions over the years. Our first work together with Professor Weiner at Purdue was to show how do we get normal dispersion mode locking on a single chip. There are two papers back to back. This one is the PRL that describes the master equation and the first observation of that in a normal dispersion resonator. We can see a number of this steadfast contributions. I'd like to point you to one, which is a recent review paper that we put up at eLight 2024 that summarizes a lot of the content, not just from our group, but the international community. So that's a good reference paper for you to look up. We have a paper that's coming up on transceivers, particularly a few terabits per second on a single resonator demonstrated. Also, this work on the femtosecond timing jitter, it's just published a month ago in Advanced Photonics Nexus. Let's start by understanding what a frequency comb is. It's an optical frequency comb that consists of equidistant spectrums, the best that mankind has achieved. It bridges from microwave to the optical domain. So if you follow the right figure, on the vertical axis is simply the intensity, and on the horizontal axis is simply your carrier frequency, optical. So from 0 Hertz all the way up to, for example, 200 terahertz. These are equidistant comb lines that it's achieved. And for example, it is this comb that allows you to synthesize, let's say, your 10 gigahertz tone all the way up to 200 terahertz. Or you can, if you have a good reference, or a high spectral purity reference at 200 terahertz or 194 terahertz, you use that to divide down as a clockwork, all the way down to your radar X-band with ultra low phase noise. In fact, the record is done with some of these frequency combs in a fiber system. Then the question is, can we make this into a small chip? So this synthesizer and this clockwork is a key part of the frequency comb. If I take a look at each of these comb lines shown in the red box, so f of n is simply a very simple integer number n times big delta, where delta is a spacing, what we call the free spectral range of the resonator of the oscillator. N times of big delta plus little delta, where delta is simply an offset when you go all the way down to 0 Hertz. The delta is otherwise known as the carrier envelope phase offset. Let me shorten that as CEP. Some people call it CEO. And that offset, if you can measure that, then you have an absolute definition of what that frequency f of n is optically, all the way defined down to DC. Well, if you do a second harmonic doubling of this red box, right? So you simply get 2f of n equals to 2 little n times big delta plus 2 little delta. Fine. You heterodyne beat that optically with, let's say, another tone of your frequency comb. If you span a full octave, right? So we'll show some of that today. Then if you beat it to the blue box and the red box, you get a heterodyne beat node of the little delta. So you have a metrology of a little delta. If you feed that back either into amplitude or phase of your pump laser, what you get then, you can lock it down using a simple pi²d loop. Then you get a full stabilization of the frequency comb. In other words, you get an absolute definition of each and every color of light in this resonator. This is number one. The second one is once you stabilized it, you can imagine that if you have a good optical reference, very clean spectral purity, you can divide it down into a microwave clockwork. 10 gigahertz, 80 gigahertz, 116 gigahertz with very low phase noise. It also serves as a timing standard for multiple applications in the field. A little bit more of that. So if I did that optical division that I described to you based on a frequency comb, you can imagine then your repetition rate then as simply your end of the comb line minus one of your references divided by the division. So if you have a larger division, you can divide down your sine omega t by, if you think of it as a Lisa noise, you actually divide down by an f-square dependence. So you improve a lot by that division from optical to microwave. I described to you the carrier envelope phase offset, the CEP. You can lock it down by f to 2f. It's known as self-referencing. And that's a key technique to stabilize the frequency tones. And as I mentioned just now, the best oscillators today are based on this laser frequency combs. There are a number of groups that has contributed to this over the years. You have Scott Diddams, Tara Fata, Fortier, NIST, Tobias Gippenberg, Carrie Vahala, and multiple people in the community. Some of our little contributions are shown down here. Again, I'd like to point you to the first one, just a month ago, showing this femtosecond clocks on a single chip. It also has applications in astrograph, that's shown in here. So understanding the wobble of some of the exoplanet systems, how do we generate even shorter pulses down to 100 altosecond in here. It has applications, the laser frequency combs has applications in strong field physics, particularly at a single cycle, a single electromagnetic cycle, but also even a subcycle work in there. In fact, one of my postdocs was looking at this before looking at this chip scale frequency combs. You can also use this for spectroscopy, whether it's dual comb spectroscopy, single comb spectroscopy. How do we understand this trace molecules at a standoff distance, detecting, again, some of these rare elements of interest. Perhaps for dreams, one interest is how do we do coherent radar? How do we coherent radar in a portable manner? How do we achieve increased, let's say, dynamic range? How do we achieve a photonic ADC that is of high performance compared to conventional microwave approaches? Some of these approaches are described in the references shown here. Let me go into one instance of this frequency cone. On the left, you see a simple ring. This is stoichiometric nitride, unannealed. So that means that there are some hydrogen dangling bonds inside. You have a waveguide that's driving this simple ring resonator like this as a start. If you simply measure its transmission using interferometry or using various techniques, you would find that there are a series of modes that's spaced by this big delta that I described to you. You also get other modes, higher order modes, maybe some dual polarization modes, maybe some crossings between the modes are shown here. So you can approximate this free spectral range by this expression, d2 omega m over dm squared, where m is simply the integer number of the modes. I'd like to highlight that there is some imprecision given by the waveguide dispersion, given by the material dispersion. So for example, the imperfection in that spacing in the cold cavity, before we drive this into parametric oscillation, into mode locking, you have this imprecision given by lambda, the wavelength, speed of light, partial to partial lambda square, and your simple Selmayr refractive index. In other words, that's known as a group velocity dispersion. We like to understand its second order because it's partial to partial lambda square, but also third order and higher order dispersions that we have to implement in our design. So GVD is something to keep in mind. Also, it's material dispersion when you get to very fine precision of your frequency combs. In the stoichiometric nitride, one can reach quality factors up to about 1 million, shown down here. So this is a loaded Q. As RJ and I were speaking about just before, this is at 1550, 1556, 1557 for this particular instance. You drive this, for example, at a high power, so that's shown in this pump laser in here, and you can actually get for mixing, but you also get parametric oscillations of this frequency cone. You will find, for example, an example of the spectrum shown down here. You can also get, for mixing, you get, in our subfield, we call this modulation instability that initiates this comb line from vacuum background, from spontaneous emission, contributing to this frequency cone. If you look at this frequency cone, just zooming in, right, you have your pump laser, let's say a narrowband pump laser, you get this cascade of beautiful comb lines that are very precisely spaced. In fact, one of our earlier works, we saw, for example, 3,600 of this modes, and remarkably, they're actually phase locked, coherently marching in step to your pump laser, shown down here. That's the spectrum. So for example, if I do different detunings, delta 1, delta 2, delta 3, delta 4, detuning meaning that the pump laser detune with your resonator modes, co-cavity resonant mode, you can see, for example, in the delta 1, it's a rather sparse frequency cone. If you go all the way to delta 4, this forest of modes starts to fill up, right? All this, you get this peaks inside, you also get the sub bands which are all filled up. Good, we like delta 4. However, if I send this simply into a germanium or InGas detector, measure its beat note, measure its tone, we call this RF tone, or even the subharmonics, and this one is at 116 gigahertz. In delta 1, actually, you get a pretty low noise RF tone. You get one of these spikes here. That means that there are two families competing for the same energy, so the same pump energy inside here. You go to delta 2, it's a bit more dense optically, but in the RF spectrum, I get 1, 2, and 3. So you get 4 families competing for the energy, looking at the nonlinear dynamics inside. Delta 3 is filled better optically. Now the combs or the subcombs have started to merge. You actually get a broadening in the RF spectrum, for example, at even 20 megahertz. So that tells us there's some breathers or something that's quite noisy in this comb. Go down to another one, delta 4, fully filled. Every of those modes are illuminated, are generated, but your RF actually has a very large noise that's appearing in your noise spectral density. So that's not so good in the RF, good in the optical. What we then do is to do what we call a hard excitation in the early works in this several years ago. If you do a hard excitation, like a jar in your excitation of your pump, you can then collapse this RF back down to its detector noise limit. In this particular case, we bring it down to about minus 120 dB, where your optical is nicely dense and fully spaced in this frequency cone. So that is an example of generating a phase coherent frequency cone to start. To understand that, it's not just optical and RF, we have to look at it in the time domain. To understand the time domain, we built a second harmonic autocorrelator. For example, in our subfield, we call this a frequency resolved optical gating to retrieve the spectral phase of the pulses coming at the detector. Here's an example of that. In earlier work, we used simply a BBO crystal, went to a waveguide now that has a larger density of states with more efficient second harmonic generation. The early work was a BBO crystal, built interferometer for that, time it with your spectrum, and you can retrieve both the spectral and the temporal data of your pulses arriving at the detector. You can see on the left, then there are these pulses appearing. This pulse train has a spacing, first of all, at 8.7 gigahertz, 8.7 terahertz, 8.7 picosecond. That tells us it's 116 gigahertz oscillator. We have the spectral information and the time information. Here's a map of the second harmonic in here, shown on the vertical axis. On the horizontal axis is the time domain. Again, your 8.7 picosecond pulses, and you have this pulse train in here, and another one on the left, and then another one on the right. If you look at this spectrogram, it has a couple of features. First, you can see these fringes are coalescing closer, let's say about 5 picoseconds. Second, you'll also notice that they're very large second harmonic signals at this wings here, right? It's very bright signal. This 2D map shows intensity as the vertical axis. So what's happening here with this very strong cone wings inside this cone? If you zoom in some more, we did a high resolution interferometric scan. This is at 4 femtoseconds timing resolution. You get this main pulse, you get these fringes appearing inside. In fact, this is a classical signature that it's actually a cavity soliton. Inside your resonator, you have this solitary pulse that's circulating, and the dynamics of that is rather interesting, and we'll speak more about that today. If you take this spectrogram, retrieve its temporal information, just the amplitude. Indeed, you achieve the 74 femtosecond pulse. Because we have both spectral and time domain data, we reconstructed the spectrogram. In fact, we had to use genetic algorithms for reconstructing this because the dynamic range was bigger than the usual elements. So we had to build this own codes to do that. When you do this genetic algorithm to reconstruct the spectrogram, you also get the spectral phase. So I'd like to highlight to you that the spectral phase is on the scale of about 1.2 or 1.3 radians when it's in the pulse. And that information is helpful for us to understand the physics of this mode locking on the single chip. Let's hold on to that for a little bit. If I look at this resonator, particularly, we know that to form solitons, you have a dispersive phenomena. I mentioned about this group velocity dispersion before, second order dispersion. To compensate against this dispersion, we need, for example, anonymous behavior in order to form a soliton, together with your chi-3 nonlinearity or third order nonlinearity. So we need anonymous dispersion. We've shown this in earlier works, generating short pulses, how they do pulse compression on a chip. So we went ahead and built an interferometer. It's a triple power stabilized interferometer with 40 femtometers of resolution. We clocked this against a Mach-Zehnder interferometer to understand for non-uniformities when we sweep the laser. We use a 40-meter delay line. We also have an absolute reference so that we know the transitions lock against your hydrogen cyanide cell so that we know the sweep and correct for that in the interferometry. Fine. When we built this and measured the dispersion of the resonator, I showed this earlier on, it's multiple modes inside. When you measure the dispersion, the higher order mode, this is transverse electric 1-2 mode, is showing an anonymous dispersion, which is D of 2.22 megahertz. Fine, anonymous dispersion. We need that to form pulses. Okay, that's a background. But when we measure the TE11 mode, the fundamental mode of that, it came up that the dispersion was actually normal dispersion. D was actually the integrated dispersion was minus 225 kilobits as a negative inside. So when we saw this, I mentioned to my team, no, this is impossible. It's not possible to form a solitary pulse with normal dispersion. Please measure again. There must be something wrong in your clocking. Maybe you reference your hydrogen cyanide cell wrongly. Do it again. We did it again and came back, Professor, it's still normal dispersion. We don't know how this could form, and this is impossible. Well, if I look at this normal dispersion, so we went back and to the drawing board and see how do we explain this phenomenon that we've observed. You do have a global normal dispersion shown in this maroon line, a slight positive nature to that. You can see this empty circles with a stronger normal dispersion. The higher order mode, as I mentioned to you, was anonymous dispersion. This is the one that canonically would form your solitons. So what's in the normal dispersion regime in the lowest fundamental mode at 116 or close to 116 gigahertz that's forming the solitons? In fact, if you look carefully, you get these little spikes in here. Those little spikes is actually an imperfection in the resonator that it's a crossing. We call it a mode crossing. That's interaction between the modes because the waveguides in the silicon nitride was not a perfect rectangle. This little trapezoid was giving a hybrid modes coupling between TE11 and TE12. That local crossing allows you to get this locally and anonymous dispersion. That is the seed. That is the initiation of the mode locking. In fact, if I zoom in some more, at let's say 1480, 1520, 1560, the dispersion or the spacing of the frequency combs in the fundamental mode is actually deviates quite a bit from your normal or conventional modes further away. This is a telltale sign that what you have is silicon hydrogen dangling bonds in your stoichiometric nitride. From Kramer's chronic, that actually gives rise to imaginary tone, which converts into a real part of chi1 or your refractive index. This actually was helpful to stabilize the mode locking. I'll describe that in the next few minutes. For example, if I measure the quality factor over the modes that I just described to you, if it's the circles, this is the one that we first used to generate the pulse. We said, well, you have this Kramer's chronic absorption that's not good for your resonator, right? Let's try to anneal it. Drive away your hydrogen bonds and oxygen, pull it away, get a better Q, get a better frequency comb. We did that. We annealed that, post-annealed, shown in the triangles. So the Q has improved, maybe a factor of 2, some even a little bit more. However, if I look at your autocorrelation, this is the original one without annealing, and you get indeed a stable mode locking on chip. But if you do, for example, and it compares with nonlinear Schrodinger's equation and some other this theory, we'll describe that later to you, they match quite well between modeling and experiments. However, when we annealed it in an attempt to improve the quality factor, since it broadens the Q over a larger number of modes, in fact, the mode locking of the oscillator becomes unstable. It becomes unstable. We were like, that's strange. Why would it become unstable on such a thing? In fact, the key word here is the filtering. In fact, this Q factor serves as an intrinsic stabilization of your normal dispersion mode locking. This narrow band of the Q factor helps to stabilize it. We draw some lessons from the early pioneers in the field. This is reminiscent of Professor Herman Haus, Professor Eric Eben, Professor Jim Fujimoto, where they did some of this in the TISAP oscillator. They call this additive pulse mode locking, or APM in short. Colleagues in Purdue and Cornell have advanced some of this very nicely in solid-state lasers. We try to replicate this in nonlinear coupled mode theory. We modeled some of this with Andrei Matsko, now at JPL. Over, for example, 121 nonlinear modes as a large set of equations. The interaction Hamiltonian is shown here. You could model this. After that, we've used a more effective method using mean field approximations, particularly Legato-Lafavia equations, to model it. If I take the nonlinear coupled mode theory instead of a full nonlinear Schrodinger's equation, you can indeed replicate in simulations your main pump and then your sidebands of the frequency combs. Indeed, fortunately, the model shows that this is a self-initiating, self-starting mode locking. After about 45 optical cycles, you do get this pulse appearing. And in fact, if I look at the model, putting in the parameters that we have seen experimentally, you do get a spectral phase of about 1.4 radians. As I said, using the frequency resolved optical gating, this matches quite well between the nonlinear simulations and our actual measurements. So this gives us confidence that indeed it is this reminiscent of APM, the pulse mode locking, that was the culprit, that was the framework to generate this frequency combs. There's more details of this inside. So for example, you can understand its chirp, its pulse width, understand a model of the CEP that I described to you, pulse energy that we can estimate from here. Between experiments, shown here is the spectral phase over your pulse width versus the analytics that we just described to you. More of the details in our paper are and I mentioned the reference papers. After that, we start to put tunability on the frequency combs. For example, you can put graphene onto that, different gate voltage on your graphene. You can tune your oscillator, let's say a reverse bias of 1.3, reverse bias of 1.7. You can form different frequency comb states, whether it's a higher harmonic, this is a fourth harmonic of your frequency comb, or you can even go up to something that is 11th harmonic of your fundamental frequency comb by just tuning the gate voltage on one side of your resonator. You can also introduce defects on purpose. So in this particular case, this is an oscillator at 718 gigahertz at a reverse bias voltage of 1.2 volts. In order to tune its repetition rate or the clocking of this frequency combs. If I look at the dynamical picture or the phase diagram of this mode locking, I point you to the top left of this chart. You have the tuning of the pump laser to your co-cavity resonator, shown down here, normalized by its 45 maximum. The vertical axis is the pump power. So for example, A squared, running from, let's say, 40 milliwatts to 160 milliwatts. What I've shown you is this maroon region, which is the dissipative solitons region that's shown here. You have a lot of very interesting chaos and nonlinear dynamics regions that I wouldn't speak about today. But there's also another region which is stable. This tiny sliver shown in the bright blue is actually what's known as the Allen-Turing patterns, which are formation of this parametric oscillations at a spacing of a terahertz. Here's the experiments to show that as I detune the pump. You can see 1 to 5 are the modes that are observed. And we can do, for example, a second harmonic again of the comb, send us into your VBO crystal, and look at its time domain. Because it's only a few of these comb lines, you get this beautiful sinusoidal oscillation of that in the intensity of the correlation. Send this into your noise power spectral density in the RF, all the way up to 2 gigahertz. From 0 to 2 gigahertz, you can see they're very clean tones at the detector noise limit, tells us that you have a coherent terahertz oscillator. We did some of the more advanced metrology, so heterodyne beats against a 1 hertz reference Menlo comb. We can say in a short manner that the imprecision of this line-to-line spacing in this particular instance, free running, it's at the level of 1 part in the 10 to the power 13 at 1 second. That's shown in this imprecision plot in here. More details are in our PRX paper shown in this particular reference. Also like to highlight that this terahertz has an interesting feature. So most of it, this is your main pump. You get a sidebands are always lower in energy. But you get this fifth state where your pump is actually lower energy than your sidebands. That means that the conversion efficiency is so strong that you get a pump depletion in experiment. That all the energy has diverted into your primary sidebands from forward mix. That is helpful under various DARPA programs currently, that you can use this to generate, again, an efficient terahertz. Here's an example of that. We send this into a photomixer together with Professor Mona Jirahi. This is a log spiral antenna. And if you drive the frequency comb, if you use the frequency comb to drive this photomixer, you get your terahertz radiation, 1.4, 1.14, 1.57, and with other frequencies also generated. At a bias voltage of 4 volts, you can go up to about 600 microwatts in this instance. We were able to go even higher. We didn't dare to amplify too much for fear of photo damage on this photomixer. But on the scale of a milliwatt, it's actually possible on this chip. You can see here, because we can tune the detuning of the pump, you can span an oscillator. You can have an oscillator that spans from 330 gigahertz all the way up to 750 in this particular instance. It can also go up to 1.28 terahertz shown there. If we do a simple feedback stabilization of the pump intensity, what you could do then is actually narrow the line width all the way down to even 100 hertz in your reading bandwidth, or if you do a VW up to even down to even 1 hertz in here. So that's actually 105,000 times improvement of the line width by just simply locking the pump intensity in here. Can do what's known as Allen deviation, particularly a fractional frequency ADAF. Happy to show that it's Allen deviation, and where tau is your integration time, you get a part per trillion quite readily in this oscillator. And it's actually very close to your counter limit, your frequency counter limits of them. So that's the first part of describing mode locking, describing a terahertz generation. I'll speed up a little bit and describe to you how do we stabilize the full comb down to 2.7 parts in 10 to the power 16 at 1 second. Here's a recent result we just got a month ago. You can see a pump in here. On the horizontal axis, now we span a full octave from 200 terahertz all the way up to 400 terahertz. These are actually dual dispersive waves, what we call a Cherenkov dispersive wave. You could see one here and another one here, because we've carefully designed the dispersion on the group velocity dispersion in multiple segments, and also the coupling. You can also notice another thing is that this has 2 pumps. right? Not just at one pump, but a second one, because we've shown in a few papers that the thermal drifts of that is driven down a lot when you have a dual pump for the resonator. It also helps in generating the soliton in a much more deterministic manner. Another feature of the spectrum is that the optical SNR is actually quite good. If I look at this, for example, at your 1550 tone, 194 terahertz, it's almost 30 dB, maybe even 40. And the full octave, all the way down to 7075 or even 400 terahertz now, you could see at least maybe 15 dB. Quite decent if you want to do the metrology of the carrier envelope phase offset that I described to you at the beginning of this talk. This is a recent result. If I look at just half an octave, how do we do the full comb stabilization? Let's spend a few minutes on it. This is the curve comb or the nonlinear frequency comb that I described to you. Then you can heterodyne beat against a fiber frequency comb. You stabilize with two tones, both your pump and your frequency spacing, because every comb, as I described in the first few slides, consists of 2 degrees of freedom. So that's this dual feedback loop, feeding back into the wavelength itself and also the intensity as your 2 degrees of freedom to your microchip. We then do the metrology of that, heterodyne beat against a 1 Hertz stabilized Mandler comb, that's the fiber frequency comb, and look at its noise character of this frequency. The first one, the first degree of freedom, is still pump. It's the strongest comb line, so we're able to stabilize your laser to about a standard deviation of about 17 Hertz. And the peak-to-peak fluctuation is 17 Hertz. The average standard deviation is about 1.2 Hertz, shown here. And then we do the second degree of freedom. You stabilize, for example, your 18 gigahertz repetition rate. When we feed back and stabilize that, you get instrument limited SSB single sideband phase noise down to about -130 dBc per hertz on this early instance. And you can see also the Allen deviation or the ADAF of your repetition rate as on the level of about 3.6 millihertz per root tau, where tau again is your integration. So this is a 2 degrees of freedom stabilization. And you can also look at this in the RF tone because of this SSB phase noise, convert that into an integrated timing jitter. What we've achieved on the single chip is on the level of a few femtoseconds of this oscillator. Another way to see this is to measure this optically. So you can measure the line-to-line fluctuations of the frequency comb when it's fully stabilized, measured out of loop with a gate time of 1 second. Here's one instance of the histogram for one comb line. You could see on the horizontal axis, you get about a Hertz level of fluctuations. Take another of these comb lines that I described to you, understand its metrology, build up a histogram. You also get on the level of a few Hertz as the maximum deviation of the histogram. If you look at the center spacing of this, it's on the scale of fluctuating of the center average, as about 53 millihertz, and you get also on the scale of 1 Hertz for each of these comb lines. That tells us that we can transfer the stability of the optical reference into the microwave at the level of 10 to the power of -16 on chip. This has applications in synchronization, that's it, photon science, spectroscopy, photonic ADC, LiDAR, and astrophysics. Let me spend the next segment on understanding the metrology of timing jitter at the KT limits, more precisely the KT square limits, and also the quantum noise limits for an 89 gigahertz oscillator. This is work that just appeared about a month ago. As I said at the beginning of this talk, you have a CW pump, you get your pulses exiting your silicon nitride chip, and you have, for example, this dispersion, carefully designed. It's not a uniform resonator. A snapshot or a cut through of this resonator shows a group velocity dispersion ranging from normal to anonymous and back again on purpose. The path average across the ring resonator, the path average GVD is on a scale of close to 0. Particularly, this particular one has -3.5 femtosecond squared per millimeter. We can generate the frequency combs in here. For example, pumped at 1600, you get a single soliton state. Matches quite well with your Dugatio-Lefavre equation modeling. That's the envelope shown in the maroon. And you also have a double soliton shown down here by controlling the detuning. Again, two solitary pulses are inside the resonator. Also matches quite well with your Dugatio-Lefavre. You can also implement one that has a defect shown in the soliton crystal, and it also matches quite well with the nonlinear modeling. Take the second harmonic intensity autocorrelation shown on the right. It also matches quite well with our modeling in here. We want to understand the noise character of this 89 gigahertz frequency cone. The first one is what we call relative intensity noise, or RIN. So we built a short delay line interferometer, measure its RIN. Suffice to say that the RIN can go down to approximately -140 or -130 dB per hertz at 10 kilohertz offset. If you're able to tolerate a 100 kilohertz offset, your RIN goes down to -153 dB per hertz. Your integrated RIN can range from 1 to 3 in the parts of 10 to the power 4. The close to carrier noise is determined mostly by the pump. Mostly there's a 1/f³ flicker frequency noise. That means that if you have a better pump laser, the resonator would simply be a good tracker of your pump laser. In fact, also the far from carrier noise is actually at the short noise limits shown on the bottom left plot here. More details in our recent paper in here. As mentioned as a fun fact, this is a single pump. Actually, when you use dual pump, you can actually suppress any of this thermal decoherence of this frequency cone. Some of the early work was shown, some of the early work on the decoherence of KT was shown in the Nature Photonics paper, but subsequently in our paper, we showed that if you use dual pump, you can do actually what's known as a thermal cooling of your resonator. That is the RIN, but also we want to understand, for first instance, its near instantaneous line width. So we built an interferometer for that, and you can also see that its instantaneous line width is mostly below 15 kilohertz, again, limited by your pump laser. We compare between the single soliton, dual soliton, and single soliton crystal. They match pretty well. The best one, it's still the single soliton that has the narrowest line width in here, just the instantaneous line width. More interestingly is to understand the timing jitter of this oscillator. You can do, for example, timing jitter PSD metrology at very high sampling rates, 89 gigahertz. So we have to build this self-heterodyne linear interferometer. It consists of a frequency shifter, number of bandpass filters, intrinsic amplifiers inside, a timing delay in order to achieve this linear interferometer. We have to use the linear interferometer in order to minimize any noise contributions in the metrology of this. As an acoustic-optic frequency shifter also. Use a Faraday mirror in such a system. We compare against the three cases that I described to you, both the single soliton, dual soliton, and the soliton crystal. Shown on the bottom left is the results of the timing jitter PSD. I'll expand on this more on the next slide. Suffice to say in this slide that the timing resolution of this interferometer can go down to about 94.2 femtoseconds per root hertz. Its RF frequency resolution goes down to about 50 millihertz per root hertz. And the frequency discrimination goes down to about 6.7 microvolts per hertz in here. If I zoom into the bottom left plot that I described to you, the timing jitter PSD. So shown on the vertical axis is femtosecond square per hertz, down to the level of 10⁻⁶, 10⁻⁷ femtosecond square per hertz for your Fourier frequency offset, right, away from your carrier. Compare this against the state of the art in the world. You have the silica resonators. We have the mag fluoride here at UCLA also. You have the silicon nitride ones across various groups internationally. And these data points are plotted together. The blue lines is the resonator or the oscillator that I just showed you for the single soliton state. In fact, you could see it's very much approaching the KT bounds, noise limits of the jitter. It's also limited very close to the quantum noise limit of this estimate. Integrated from 10 kilohertz to 1 megahertz, this soliton mode-log laser has an integrated timing jitter of about 1.7 femtoseconds. Again, very close to your thermodynamical and quantum noise limits. Because we use a self-heterodyne linear interferometer instead of direct photon detection, we're able to avoid AM to PM conversion, amplitude to phase conversion. It also improves your short noise limits far from carrier. More details are shown in this paper, as I described to you, the theory behind this, the estimates of the model, how we did the experiments. And when we integrate the jitter, it's shown in this maroon line or this purple line. It's on the scale of about 1.7 femtoseconds. We also did the modeling for the noise characteristics in here. It's actually non-trivial because, as I described to you, the resonator is not a uniform ring resonator. We had to design its dispersion carefully. So we did is what's called the IKEDA non-mean field theory modeling, nonlinearities plus noise inputs inside. We had to run this on multiple processes, do some speedups on the computational side, include Raman noise, include the avoided crossings that I described to you, include also different factors of thermal noise inside. We're happy to say that the modeling captures a lot of the key characteristics of the experiments. And you also get to, on the scale of about a femtosecond in here, for different dispersions of the global dispersions of the resonator. In the last few minutes, I'd like to describe to you a reference clock for the frequency cone. How do we achieve sub 10 hertz per root hertz compact lasers on chip at the KT square limits? For example, you can start with a mag fluoride single crystal. This is together with our colleagues at OE Waves, Andre Matsko and Luke Melaki. Shown down here is the frequency shift versus temperature, right? It's TEMCO on this resonator. A conventional resonator has a large frequency shift of about 10 kilohertz when you get a 5-degree fluctuation of temperature. So it's quite worrisome. What they did together with us under a DoD program is to do this compensated resonator. So it's this zero-deer sandwiched with your mag fluoride single crystal resonator. You get less than 1.5 gigahertz shift over 5 degrees Celsius. That's helpful. In fact, with this compensated resonator, you can measure it or estimate theoretically first its frequency noise versus Fourier frequency offset. You get indeed quite a significant improvement, for example, over its thermal expansion noise, its TRN or thermal refractive noise, also it's improved in this system slightly. We can measure then its frequency noise doing metrology on a 1 hertz laser. Shown here is the frequency noise PSD. Free running, it's shown in this black line. If you do an ejection lock laser to this reference cavity, or you can also do a PDH, a Pondriver Hall lock loop to that, you can measure, for example, the green line is the frequency metrology of that. It's close to its TRN. Do the beta separation line to estimate its line width. On the scale of long time in line width, it's on the scale of about 100 hertz. If I zoom in to its frequency noise PSD, I'd like to point you to the right plot in here. This is your thermal refractive noise limit. Your measurement are very much close to its TRN at the level of 1 hertz and 10 hertz offset. Now, you can see a lot of fluctuations on this scale. In fact, acoustic noise starts to come in. In fact, pressure fluctuations of the ambient starts to come in. Some people even say humidity starts to affect this resonator. We put this in vacuum chamber. Long-term ADAF is shown down here. So for example, at 100 milliseconds, this particular reference cavity has an ADAF of about 10 minus 13. In other words, you get about 100 hertz of frequency shift when you measure this at 100 milliseconds. This long-term drift, there are ways to compensate for this. Happy to discuss this with you. You can do better to improve the long-term ADAF, the last 2 or 3 slides in here. For example, you use dual polarization, right? You have a TM and a transverse magnetic polarization. Both share similar characteristics of the drift. If you build a dual loop for that, we have shown that you get a 51 times improvement in the long-term ADAF, for example, even at 1,000 seconds. Important for some flight missions in here. We also measure, for example, the frequency noise down to very low frequency offsets. I mentioned the 1 Hertz previously. If you measure down to 0.1, 100 millihertz, 100 millihertz, 10 millihertz, or even 1 millihertz, you would see that there's a lot of random walk in here. So there's a lot of technical noise to examine. Overall, if I'm interested at the level of 10 kilohertz offset, happy to say that this particular reference cavity has a 20 hertz per root hertz of frequency noise PSD in here. With that, these are the team members who have contributed to the discussion or the work that's presented today. And the funding agencies with DARPA, NSF, multi-university research initiatives, different fellowships, some of the foundries in Singapore, angel investors, early stage investors, national labs, companies, NASA, and also the NIH. With that, I'd like to thank you for your attention.
Thank you, Chivoy. This was an insightful presentation. Quite a lot of details, quite a lot of work. I mean, it's an enormous amount of work that you have highlighted here.
Thank you.
And you have been trying to shrink that down into 50 minutes. I mean, that's incredible. Thank you. So we now have some time for questions. So please feel free to unmute yourself and ask questions, or you can post your questions in the chat, and Chivoy would be able to answer those. Steve is also online, I guess. I see Steve there.
Hello, I was in transit, so just ignore me. Thank you.
Okay.
But thanks,
Okay.
Chivoy.
Hi, Steve.
So it seems there is no questions here. Then in that case, maybe Amy, you can actually post your slide. I had a few questions, but I will ask you later, Chivoy.
Sure. Do you want me to go to a particular slide?
No. I was asking Amy
Okay.
to post her slides.
Sounds good. Sounds good.
Okay. So this is the seminar series for the upcoming weeks. Next week, being the week before Amy, can you go to the next slide? Yeah, the next week being the Memorial Day, we don't have a seminar on May 23rd, next Friday. But following week, May 30th, we will have a presentation from HRL. Min Nguyen is going to give that talk. And please go back to the previous slide, Amy. Yeah, for those who want to register, please do register. There is this code here, and you can go and register to those if you want to receive your emails, personal emails. Okay, thank you so very much. And Chivoy, once again, thank you.
No problem. Thank you. Yeah.
Thank you, everybody.
Bye.
Bye-bye.
Have a nice weekend. Yeah, bye.